So what do we need to do today? Let's go to the website. And all right. So I have rearranged the video a little bit so that it can fit the schedule that we are going. So I need to do Markov chain and sufficient statistics. But I have all the videos here. I checked the video qualities are good, so I hope you can follow it. And there are lecture notes right on the side. So probably I would like to discuss this one as well today. So let me download this. Okay. All right. So if you know information theory, you can apply to many different problems. One of the problem that you can apply if you have done the homework number one is to is a Bitcoin. When you heard about mining of Bitcoin, basically you are making use of homework number one, the first problem. Okay, so I will just illustrate it a little bit. Okay, so how many of you invest in Bitcoin? Probably that person might know better than me about this, okay? So about mining, right? So basically there is something called hash algorithm. Hash algorithm can be defined as a function from a file space to 256-bit space, okay? From a file to a 256-bit number, okay? So file means in digital world, file is a number, okay? File is a number, okay? This digital file, if you put this into digital form, it is a number, okay? So so how big is this number in terms of Bitcoin? There is a block header and there is a block body, and the block header. This is about 1 megabyte. 1 megabyte. So 1 megabyte is how big in terms of binary number? I mean binary representation. Mega is 10 to the 6, right? And byte is 8-bit, right? So this is 8 million bit, okay? So 8 million bit. So basically a file is a 8 million bit representation, okay? So how many different files do you have in this space? How many different files? How many different files? Okay, thank you. 2 to the 8 million, right? Right? Don't deal with the teeny-weeny detail. Like 1 byte is 1024 bit rather than 1000. Don't challenge me with those teeny-weeny details. Okay, I'm just taking the order of magnitude, how big they are, right? So there are this many inputs that are possible, and then each one of them is a file, right? And basically, if we call this set X, the size of this set alphabet size is this one, okay? Size of this alphabet is that one, okay? That's what I'm saying, okay? And then hash algorithm, this hash algorithm, secure hash algorithm actually, is a 256-bit representation or summary of this file. Okay? So if you take a particular file, map it to a number space, which is much, much smaller now because it is only 256-bit. Okay? So there are hash values. This, if we take a look at a particular hash value, it looks something like this. Something like that, 256-bit. Okay? So how many balls do you have here? How many balls do we have? Same song and dance, so it is 256 bits. So you have this many small balls, okay? So if you take one file, map it to this space, that's what is happening, okay? So since this file is very big and this number is relatively short, they call this summary of a file, okay? And basically, they use this to represent a file. Or when you type in login password, right? When you register to a server, if you type in your name, it will translate to this summary, okay? And then when you next time log in, basically the server has your summary of your name. So if you type in your name or the password, then it checks if the summary stored in the server is the same as the summary that you just typed in, so that it can identify, this person knows the password. But since the server has only the summary, right? Server, the administrator cannot figure out the true password that maps to this, okay? So that's used in the security, authentication, and so on. So hash algorithm is very useful, and basically Bitcoin, Satoshi Nakamoto has used this hash algorithm to design the mining problem. Okay, and then mining problem, once the difficulty level is set, then there are millions of mining nodes on the internet trying to find out the right answer. You will understand that one if you read this document. Okay. And then, based on this, node, you can, since you understand the information theory, if you have taken the whole course, basically you can design your own proof of work mining algorithm as well, new ones. Okay. All right. So basically, this hash algorithm has this type of characteristic. So for example, if you type in this information, you can see it, right? Is it too small? You can see, you can read it, right? Information theory, 2019, GIST, Heung-No Lee, right? And then the hash algorithm gives you this summary of this text. And then this one is Hexar representation. So Hexa means you group 4 bits into a hexa number, right? A hexa number is a number where you have a 16 alphabet, right? 0, 1, 2, 3, all the way up to 9, and then A, B, C, D, E, F, right? So you have a 16 alphabet, okay? That's a hexa representation. Basically, that's this one, right? So 0 hexa here means 0, 0, 0, 0, right? 7 here means what? 0, 1, 0, 1, right? Like that. So it is a hexa representation. So in terms of hexa, how many hexa digits do you have? 256 divided by 4, right? So 64 hexa digits. So this is equal to 256-bit representation of this file or message, the input to the hash algorithm. And then the characteristic of this hash algorithm, by design, if you have a little bit of a difference, like in this case, I have put a comma right here, comma, then you get the hash output that is completely different from this previous hash output. Only a teeny difference, single difference. Then here you have a huge difference. As you can check, this one and this one is not related at all, right? Completely different. This one is done by design. Why do they use a hash algorithm designed this way? Anyone can tell? Sigmin? Why do you think they have designed the hash algorithm this way? Huh? So what is any other person? Security. So can you add a little bit? Why it becomes secure? Secure means in terms of what? Yeah.
So someone has a key.
There's no key here. There's only input and output.
No, but I mean, it's easy to generate, but it's really hard to degenerate.
Yeah, that's good. Yeah. That's good. So going forward is easy, right? If you put this one of these file into this function, hash function, and then it generates output, which is this summary. Okay. So going forward is easy. You just do the number of multiplications and additions, take the modulo operations, then it becomes that. But going backward is almost impossible. Almost impossible. That's what it is. Okay. So by design, they want to have a forward-only function. Okay. No backward. From knowing the summary, if you have a backward computation is easily done, then servers save the hash of your login ID and password. Then any administrator that controls the server can decode your password and user ID and bank account and so on, right? So that's what your answer. Okay. So by design, this is a forward-only function, right? And is there any other problem that you can, any other characteristic that you can say here, right? Do you see any problem going from bigger space to a smaller space? Then not one-to-one. Huh? So what type of function this is? Is it a function? It is a function. So since this is small, if I exaggerate, right? This space is small. I have 4 balls, right? And then here I have 16 balls, right? 16 to 4 balls, right? And then each one has a summary, right? Each one has a summary. If I need to find the summary, but this is the target, I mean the balls in the range space, then I have to do this, right? Right? I cannot but do this, right? So this is many-to-one mapping, right? Many-to-one mapping is not called a function, right? One-to-one. Many-to-one mapping is okay. Let me take it away, right? This is not a function, right? If you have 2 different mapping, right? But this one is okay, but this one is have a problem when you want to go back, right? So 한국말로 말하면 이게 어떤 문제지? 쫑난단 말이지. 너무 쉽다 이렇게 얘기하면 그지? So this is a collision, a lot of collision, right? Collision can happen, but this number is very big. I believe it is the 10 to the power of 80, right? This is the very big number, so that no collision actually occurs in practice. Even though you have too many fires, right? This ball, you know, you can never hit a case where there is a collision, okay? Because this number is too big, okay? How big is that? It is like the same order of magnitude that the number of atoms in the universe, in the whole universe, okay? So this collision in theory exists, but it never occurs in practice. So that's why they use this hash algorithm, okay? Okay, so there is no hash collision has occurred so far, okay? And then it's not going to happen in the future as well. Not at least not near future, right? 10 or 100 years is not going to happen. Probabilistically, the probability of a collision happens is very, very small, 10 to the minus 40 or 10 to the minus 60, something like that. So basically, that is the property of this SHA algorithm, okay? And it is made of this multiplication and additions and taking the modular operations and so on. So it is almost impossible to go back, okay? And proof of work in Bitcoin is using this, okay? So it is very simple, actually. So, okay? So because this is too big, let's make it smaller, and then we will extend it. Let's say, let's do a 8-bit summary. Suppose you are using only the first 8-bit of the hash output. So in this case, how many balls here do you have? 256 balls, right? Okay, all right. And then I will design a POW problem, proof of work, right? Proof of work, and I will design my target size. Let's say each one is a number, right? So from 0 to 2 to the power of 8 minus 1, right? 255, right? Starting from 0. And then I say that what is 2 to the power of 7? 128, right? So let me have a target of 2 to the power of 7 minus 1, which is 127, okay? So I design a problem, right? What is the hash output from this space, right? Is smaller than this number. So I can ask this question, right? What is the probability that hash output from this space to be compared with 127? Can you say about this probability? So how many possibilities? So there are 256 balls. Let me ask you this way. So there are 4 balls only, 4 balls here, right? And then I select one ball. Basically, that is taking a particular input and getting the hash output, right? That is like equivalent to saying that take one ball from this space, right? Okay? Because that mapping, right? And then what is the probability that the first ball was selected? There are four distinct balls, right? 4분의 1. 누가 말했지? 그렇게, 그럼, 됐죠? 그러면 여기에서는 2의 8승계의 볼이 있어요. 그런데 이 2의 8승계의 볼 중에서 해시 아웃풋이 127보다 작거나 같을 확률이 뭐냐 이거지. 2분의 1. 2분의 1이지? 에? 누가 말했어? 에? 뭐라고? 크게 말해줘봐.
당연히 절반이야.
왜 절반이죠? 256개. 그렇지. 256개. 요거는 총 256개의 볼 중에서, 그죠? 지금 몇 개를 뽑는 거죠? 128개. 그죠? 자, 그러면 내가 이번에는 숫자를 바꿔요. 2의 6승 빼기 1로 하자. 그래서 여기를 계산하기 쉽게 얘는 2의 8승이고 2의 6승 빼기 1개로 합시다. 그러면 얘 뭐예요? 2의 6승이 되고 4분의 1이 되겠네. 그죠? 그지? 그러면 뭐 5로 바꿉시다. 그러면 여기 5로 바꾸고 8분의 1 되겠네. 이렇게 되겠죠.
그 왼쪽에 있는 애가 오른쪽 공에 이제 정확히 오른쪽 개수 남은 거 애들이 하나에 매핑되어야 그게 성립한 거 아닌가요?
네. 근데 우리 그 아까 해시 펑션의 특성이 여기에서 매핑 되는데 어디로 매핑 되는지 모른다 그랬잖아요. 막 뒤죽박죽 된다고. 빛 하나만 바꿔도 어디로 갈지 모른다 그랬잖아요. 그러니까 그거는 랜덤하게 내가 이 바구니에서 공 하나 뽑을 확률하고 같게 만드는 거죠. 재밌죠, 이게. 재밌어. 그런 특성을 가진 게 해시 알고리즘이니까 사토시 나카모토가 그 특성을 이용해서 이제 작업 증명 알고리즘을 만든 거예요. 그렇게 해서 하면은 이제 본래 문제로 돌아가면 자 2에 256이다. 그죠? 2에 256이요. 네, 2에 255부터 합시다. 그러면 2분의 1. 그죠? 2에 255승. 그러니까 2분의 1. 근데 254로 바꿉시다. 4분의 1. 253으로 바꿉시다. 8분의 1. 이러면서 계속 작아지겠죠. 그죠? 그런데 요거를 그림으로 그려서 하면은 이렇게 되는 거야. 여기를 이제 256개의 비트인데 첫 번째 비트가 0이고 그 나머지 비트는 뭐가 돼도 상관없음으로 하면 2분의 1이죠. 그죠? 첫 번째 비트를 0으로 한정시켜 버렸고 독립 베어리어블은 255개밖에 없잖아요, 이제. 그럼 2분의 1. 그 다음에 얘를 0으로 바꾸네. 두 개를 고정시켜. 그죠? 그러면 what is the probability of fx smaller than this number? 이렇게 물을 수가 있고 그러면 4분의 1입니다. 8분의 1입니다. 16분의 1입니다. 혹은 이 앞에 0의 개수를 x개라고 하면 이 probability는 x라 그러면 안 되겠네. m개라 그러면 0의 개수로 m개라 그러면 아하 얘는 2의 마이너스 m승입니다. 이렇게 하겠죠. 그죠? 2의 마이너스 m승입니다. 그러면 m이 256까지 붙을 수가 있으니까 you could have 256 digits and let's say the number of zero digits in the first place is let's say 10, right? You can do that, right? And then 20, 30, 40, you can do that, right? So that as you can do that, basically the probability of a single hash output and then satisfying this condition becomes very, very small, right? You can design, right? And then let's call this small p, right? Let's call this small p, right? This is like if you take one ball from the big space and then getting one output, which is this mapping by hash algorithm, right? And then basically this set is divided into two different sets. Success set, failure set. How do you define the success and failure? If you satisfy this condition, satisfy success. Failure, if it is not, right? So that is a hashy success. You take one file, hash output, and then see if this satisfies the condition, right? Then success. It's not satisfied, failure. You can design like that. Then you can make this into, let's say, 40, 70. Currently, Bitcoin here is 2 to the power of almost 70. 2 to the power of minus 70. So how big is that number in the, you can calculate it, right? So in this case, Bitcoin designed the difficulty level so that there are large number of nodes independently finding this hash output for a particular block, right? Let's say there are, let's say, 2 to the power of 10 nodes, right, working independently, right? Then it requires almost like a 2 to the power of 30 hash cycles. You have to repeat this experiment again, again, and again, and again by changing something called nonce, which is a counter. So you keep the same content, then but change the nonce value. This is works as a counter. Let's say 0, 1, 2, and then you change this single digit, right? As you have seen the property of the hash algorithm, the hash value changes randomly, right? In a random fashion, so that you can, try to find out a hash value that hit the success, right? Okay, so that's POW algorithm. And then I have given you, in terms of this number of 0 first digits, but in general, you can set this as any binary number. So you can just say it as a target. So we have not only twice, difficulty level change, but very smooth change. Okay. So if that is this one right here, so proof of work and it's a success. So given a target number between these two number, then basically you have a target. Then you can you basically have drawn a line between the two different sets, success set versus non-success set. And then there are lots of words. And then currently they have designed ASIC miners doing just this experiment again and again by changing the nonce changing the timestamp a little bit in order to hit as many as hash output for the same block body, right? Until you find a success. Basically, this Nth minor S9, almost $3,000, like 2 years ago, because I have given this lecture maybe 3 years ago, right? How fast this machine can find out the hash output of a Bitcoin block body? It says 14 terahashes per sec. So tera is 10 to the power of 12. So this machine can get the hash output per 1 second 10 to the power of 12. 1조 개의 해시를 뽑아볼 수 있어요. 1초에. 그렇게 빠른 머신이 나왔어요. 이런 머신이 밀리언 개 이상이 작동을 해야 아까 2 to the power of 70 프로블럼을 10분에 찾는 노드가 한 개씩만 나오게 할 수 있어요. 그래서 처음 해시 값을 제대로 찾은 사람, 석세스를 히트한 노드가 비트코인을 리워드로 받는 거예요. 비트코인.
그게 채굴의 의미인가요?
그게 채굴의 의미. 재밌죠? 인포메이션 티어리 알면 할 수 있는 게 너무나 많아. 할 수 있는 게 너무나 많아. 그래갖고 난 우리 학생들이 다 인공지능만 하겠다고 그래갖고 너무 답답해. 진짜 그거 매핑 펑션 하나 디파인 한 거잖아. 인풋 들어오면 매핑해서 아웃풋 뽑아보는 거잖아. 그걸 예전보다 잘 뽑아보는 건데 데이터를 막 때려박아가지고 트레이닝 시켜갖고 얻는 거잖아. 학생들이 생각할 게 아무것도 없어요. 구글 엔지니어가 한 거 그냥 다운로드 받아서 쓰는 거잖아. 그런 데다가 시간을 쏟으면 안 돼. 더구나 대학원에서는. 자, 그래서 랜덤 엑스페리먼트를 자, 그러면 우리 호목 넘버 1하고 내가 연결을 시켜줄게요. 그러면 호목 넘버 1에서 뭘 했어요? 버놀리 트라이얼 했잖아. 그래갖고 K번째 석세스 나오는 거 했잖아요. 그죠? 그러면 아까 내가 말했어요. 10분 안에 비트코인 그 네트워크에서 밀리언 개의 노드가 계속 해시 뽑아보는 짓을 하고 있는데 그 중에서 한 노드가 성공할 확률 그런 걸 계산할 수가 있다고. 그러면 그거를 난이도를 내가 만들어가지고 타겟 밸류를 조정을 하는 거야. 그래서 이 타겟 밸류를 헤더에다가 써놔. 그러면 내가 노드들이 풀어야 할 문제를 정의해 놓는 거야. 얼마나 어려운 문제를 풀어야 되는지. 그죠? 자, 그 이야기를 할 겁니다. 그래서 definition, Bernoulli trial with success probability P. 한 번 뽑는데 성공 확률이 P래. 그죠? 근데 이게 원래는 한 번 뽑았으면 repetition이 아니잖아. 그지? 근데 볼의 개수가 너무 많아갖고 to the power of 256. 그래서 쫑도 안 나는다라는 거잖아. 그러니까 그냥 얘는 independent trial이라고 봐도 된다고. 이렇게? 너무 커서 숫자가. 그러면 let target be given such that a number between these two and with a single selection of a file X from this big space and we obtain the summary Y in the small space 2 to the power of 256 and then the output Y in the hash space belongs to either event of success or event of failure. 그죠? 아웃컴인데 그 아웃컴이 success set에 속할 확률, failure set에 속할 확률. 그죠? 됐죠? 그러면 버널리 익스페리먼트가 딱 정의가 돼버렸잖아. 타겟 밸류가 정해지면 난이도도 정해졌고. 오케이? 자, 그러면 이거 이제 해시 아까 지금 내가 보드에다 설명한 거. 그러면 size of this alphabet, right? This set. collection of all y satisfying this relation and the size of the whole output set, the size of the alphabet of y. 그러면 이렇게 됐죠. That is the single success probability. And then now I want to find out, what is the probability that the the mining machine find the success hash, right, within k trials. 이런 문제 낼 수 있죠, 그죠? 그다음에 what is the probability that the computer finds the hash value, the success hash value at the exact time point where time point is measured as a slot, let's say k slot, kth slot. 이런 문제 낼 수 있죠? 그러면 given single success probability, what is the probability? So I define a random variable, let's say capital K, that is a random variable representing the success, okay? And the K is equal to small k, and then I ask you to find the probability. That is exactly the homework number one, problem number one problem, right? So given this Bernoulli trial, then basically probability of K is equal to small k, right? The K is running from 1, 2, 3, and so on, all the way up to K, the largest K, basically infinity, right? And the K is the random variable. And then basically, like, this is the success exactly at the kth trial, right? Then all the previous trials, you should have failures, right? You have picked the hash values in the failure set for all k minus 1 of them. That is this one. And right at the last moment, where kth trial, you have a success. So k minus 1 failures, and the kth trial, you finally success. That's this probability, okay? And then what is the probability of capital K smaller than or equal to time slot K, right? Then basically you do this using the technique that you learned in homework number one. You can calculate this, okay? All right, so basically, and then after you have done that, this is a geometric distribution, right? They have named it because it occurs in reality many, many times. So basically, you use this and you can find the expected value, right? 1 over p, right? So this is the average number of hashes output that you have to see until you hit the success, right? By one computer, okay? And then the variance of this, right? Now you know the speed of hash output, calculation, right? 10 to the power of 12 hashes per sec. Then you can calculate. You can make this related to real time, right? Okay, using a particular CPU or GPU or the mining machine that I have shown you, right? You can relate this to the time that it requires to solve the problem, right? Yes? Okay? So basically that's it. And then if you are interested in, you can read it further. So I relate this to the continuous time. So basically I can talk about that is exponentially distributed. Once it is exponentially distributed, then I can analyze the double spending problem in Bitcoin network as well. We have a paper published in that area 3 years ago. So basically, there is a homework and so on. As you can see, that is exactly the homework number one. And then I can ask entropy questions, mutual information, and so on and so on. Okay? But I'm not going to ask you to do this. Okay? I'm just trying to give you motivation, right? You learned mathematics in class, proving what's already known to be true or false. Easy. Can you apply to your problem, your research problem? And then even if you do artificial intelligence, can you apply the data processing inequality problem that you learned in class? Can you apply to your problem? That's what you needed to do, okay? All right, so, but those people in my laboratory need to do this homework, okay? All right. So basically that's the motivation. And let's now go to this lecture note. I would like to do sufficient statistic a little bit. Maybe not this one, a little later. So basically I will do this first. Easier one first, okay? So here, 이거가 아닌가? 이건 다 한 거지. 다운로드를 또 해야 되나? 없구나. 오케이. 그러면 거기로 가서 방사가 돼서 요거죠? 요것도 저장을 해 놔야 되겠네. 컨트롤 L인가? 안 되네. 웹사이트에서 열어서 그러구나. Okay. So here I need to talk about Markov chain. You guys should know Markov chain by now, right? So how do you define Markov chain? Basically this word, right? Conditioning on current, future, and past are independent, right? So, but in terms of notation, maybe we can say there are three random variables, x, y, z. x to y to z is called the Markov chain if this it is satisfied. But the meaning of this in my note looks very simple, but when you actually try to apply it, very complex, right? So for each z, x, and y, you have to apply, okay? And note it implies that if you have a joint probability x and z given y,